In the last video, we talked about this idea of an implicit function, which is just a relationship that's implied between two variables that make up some sort of dimensional space that comes as a result of collapsing one of the dimensions of the space in which it exists. And if that's confusing, I highly recommend you go back and watch the first video, because in this one, I'm just going to do a bunch of practice problems where we get a little bit of exposure, not just to implicitly defined functions, but also to, or primarily to, implicit differentiation. And so in this video, we're really going to explore that idea of differentiating functions implicitly and seeing how that's useful to deal with functions that would otherwise be very hard to deal with. So let's take this idea and let's apply it to a couple of examples. But I was careful to pick some examples here that would further our understanding in the world of calculus. So for example, we're going to use implicit differentiation here to solve for the derivative of the natural log of x. You'll recall that if y is equal to the natural log of x, you could raise both sides here. You could raise e to the power of both sides here. I think that's the way you said that. And we would get e to the power of y is equal to x. And now we can use implicit differentiation because this is very easy to take the derivative of this. This is just equal to e to the power of y. But remember, y is implicitly a function of x, so we have to use a chain rule here and multiply by the derivative of this inside function here, y, with respect to x. And then we'll take the derivative of this side. This is just the derivative of x with respect to x. It's just equal to 1. We can finish this out. This is dy dx is equal to 1 over e to the power of y. And now if you want this you want to use implicit differentiation to solve for the derivative here, but we can plug in our original definition to make our derivative explicit, so to speak. And so we could take our value for y here, and just plug it in for what we have there. And what we'll get is that the derivative of y with respect to x of the natural log of x is equal to 1 over e to the power of natural log of x. That's just 1 over x. And so that's our derivative of the natural log function. And we could do a very, very similar technique here with the derivative of logarithms of any base. This is y is equal to the log base a, so just some general base of x. We could raise both sides. We're not raising both sides to the power of a, we're taking a to the power of both sides. That's the way to say it. I very much want to say raising both sides to the power of a, but that's not what's happening. So we take a and raise it to the power of both sides of this equation. It's not changing the value. The right side just becomes x. The left side becomes a to the power of y. The derivative here is just going to be, we'll take the derivative of the outside function with respect to y. It's going to be the natural log of a times a to the power of y. But now we need to take the derivative of this inside function, this y, which is implicitly a function of x, written explicitly up here, so you know that it depends on x. We'll take the derivative of that inside function with respect to x. Once again, just exercising a chain rule. Take the derivative of the right side with respect to x. This is just equal to 1. And now we solve algebraically for the derivative. We get the dy dx is going to equal 1 over the natural log of a multiplied by a to the power of y. And here, once again, we could just plug in our y is equal to natural log of base a, not natural log base a of x back into this equation to get a explicit form of our derivative. And we would get that dy dx is equal to 1 over, and a to the power of log base a of x is just going to be x multiplied by the natural log of a. So this is the derivative of logarithms with any sort of arbitrary base a. Another problem here that will let us get some practice with implicit differentiation is showing that the power rule, or x to the power of n, the derivative of that being n times x to the power of n minus 1, showing that that power rule holds for fractional exponents. I remember in a previous video I proved that the derivative of the square root of x was equal to what we expected based off of the power rule. But I didn't show that this is true for all forms of fractional exponents. So if you have that y is equal to x to the power of m over n, is typically how this is written, I need to prove that this is true, that what the power rule says for all of these different cases. And the only way to do that is to use implicit differentiation, which is why I held off on it until now. But really, we can raise both sides here to the power of n. And if I raise this to the power of n, that's just going to eliminate that n and that exponent. And if I raise this to the power of n, it's just going to become y to the power of n is equal to x to the power of m. And now I can take the derivative of both sides. We would get the derivative here is equal to ny to the power of n minus 1 multiplied by the derivative of y with respect to x. This would be equal to mx to the power of m minus 1. And now we could solve for the derivative of y with respect to x. This is equal to mx to the power of m minus 1 divided by ny to the power of n minus 1. And now we just need to plug in what our y was from the original story. Y is equal to x to the power of m over n to get it into an explicit form. This is equal to, and I'll factor out this m over n here. And we would have x to the power of m minus 1. So our y is x to the power of m over n, x to the power of m over n to the power of n minus 1. And then this is just a matter of multiplying these exponents and then subtracting. And so we would have that this is equal to m over n times x to the power of, let's see, we would have m minus 1. I'll put that in parentheses, minus, because we are dividing here, m over n times n minus 1. M over n times n minus 1. And you can put this whole thing in parentheses. And then we really just need to reduce this here. And so we have m minus 1 minus, and we can do this multiplication here. That would be, let's see, that would be m, because those n's would cancel, and then we would have minus m over n, minus m over n. And then we would distribute this negative, and we would get that these m's would cancel, and we would add this, and this would be m over n minus 1. And so our final answer here would be m over n times x to the power of m over n minus 1, which is exactly what we would expect based off of our power rule. So yes, using implicit differentiation, you could prove that this power rule holds for fractional exponents, any sort of exponent that could be written as a fraction. So any sort of root, any sort of cubed root, anything like that. So in order to wrap up this video, we're going to talk about the inverse trigonometric functions, because that's another great example of where you can use implicit differentiation in order to solve for these derivatives. Inverse trigonometric functions are just a way of undoing the trigonometric functions. So for example, the inverse sine of x is just going to be equal to x. I don't know why I put that in double parentheses, but that's just what these are. And so this is a great candidate for implicit differentiation, because we could just take the sine of both sides. We get that the sine of y is equal to x. And this is very easy to differentiate. It's just going to be cosine of y, taking the derivative of this with respect to y, and then multiplying by the derivative of y with respect to x, just using that chain rule. And then here on the right side, we have the derivative of x with respect to x. That's just going to be equal to 1. And then we take the derivative of y with respect to x and solve for it algebraically by dividing both sides by the cosine of y. And then we can plug back in what our definition of y was from the beginning if we want this derivative in explicit form. And we would get 1 over cosine of the inverse sine of x. And this is 100% correct. If you plot this on a graphing calculator, it will coincide with the derivative of inverse sine of x 100%. This is an accurate way to write this. But there's another way to write this that's a little bit more common, just because it's a nicer definition. And it involves going back to this cosine of y here and just using our Pythagorean identity, which tells us that cosine squared of any variable, but in this case we're dealing with y, plus sine squared of that same variable is equal to 1. And if you solve for cosine of y here, you will get cosine of y is equal to the square root of 1 minus sine squared y. And the reason that this is useful is because in this case we're dealing y is equal to the inverse sine of x. So if cosine of y is equal to the square root of 1 minus sine of the inverse sine of x, squared, as that's what sine squared is, then this is just going to reduce very, very nicely to be equal to the square root of 1 minus x squared. And so if we plug that in for cosine of y here, that's the same as saying that this is equal to 1 over the square root of 1 minus x squared. And so these are both ways to write the derivative of the inverse sine of x. I would say that this one is just a little bit more common, but if you have a graphing calculator and you put both of these equations in, you will see that they overlap 100% accurately. And the derivative of y is equal to the inverse cosine of x is very, very similar. We just say that cosine of y is equal to x. Take the derivative of both sides. We'll take the derivative of cosine of y with respect to x, but first we take the derivative with respect to y. That's going to be negative sine of y multiplied by the inside function, the derivative of that with respect to x, dy dx. This is just going to be equal to the derivative of x with respect to x, which is 1. We have that dy dx is equal to 1 over negative sine of y, and so this is equal to 1 over negative sine of the inverse cosine of x. But similarly, another way to write this is we could use our same Pythagorean theorem in order to solve for sine of y, and that's going to be equal to 1 minus cosine squared of y, taking the square root of that. And so if we have negative sine of y here, that's just to say that this is dy dx is equal to 1 over negative square root of 1 minus cosine squared of y, and then we plug in y here, which is equal to the inverse cosine of x, and so this winds up being equal to 1 over, or negative 1 over the square root of 1 minus x squared. And so that's our derivative of the inverse cosine function. It's going to be this one. And it really is just a negative derivative of the inverse sine function, interestingly enough. All right, let's do the inverse tangent function. This, once again, we'll just take tangent of both sides. We get that tangent of y is equal to x. And then taking our derivative here, the derivative of tangent from the last video is equal to secant squared, and so we'd have secant squared of y because we're differentiating with respect to y first. Then we differentiate the inside function, this y, which is implicitly a function of x. We differentiate that with respect to x and multiply it because that's the chain rule. And then here we have derivative of x with respect to x. Once again, it's just 1. We have dy dx is equal to 1 over secant squared of y. And once again, you could just plug in our inverse tangent here and you could be done if you prefer it in that format. But there's another way to write this. Tangent squared of theta plus 1 is the same thing as saying sine squared theta over cosine squared theta plus 1 is the same as cosine squared theta over cosine squared theta. And so this is sine squared theta plus cosine squared theta. That's just equal to 1 divided by cosine squared theta. 1 over cosine squared theta is just secant squared theta. And so here on the bottom we have secant squared of y. We can rewrite this as 1 over tangent squared of y plus 1. Those are exactly equal. And then when we plug in our inverse tangent here, this becomes a little bit nicer. We get 1 over x squared plus 1. And so this is our derivative for the inverse tangent of x. Now, I debated whether or not I was going to include these derivatives of arcsecant, arccotangent, and arccosecant in this video just because they're a little bit more complicated. But there's a little geometric tool that we can use here to make these a little bit more simply. So I think I was just going to put them in at the end of this video because I do think they're, we're really in the home stretch here. These are the last 3 functions. And so this starts the same way as the previous ones. We're just going to take secant of both sides here, and we'll get that this is equal to the derivative with respect to x of secant y. Secant y is equal to the derivative with respect to x of x. This is just going to be equal to 1. And then this, just like in the other ones, we're going to get tangent of y, secant of y, multiplied by dy dx. And then here this is going to be equal to 1. Now, I actually don't want to leave it in terms of this. When we were originally differentiating secant of x, we used the chain rule, or the quotient rule. and we said that secant of x is equal to 1 over cosine of x. Or maybe we use the chain rule with the negative exponent. I think that's what we did. But the original answer that we got was sort of that you could think of this as tangent of y is equal to sine of y over cosine y. This is 1 over cosine y, and so this is equal to sine of y divided by cosine squared of y. This is originally what we got. We just broke it up to make it a little bit nicer and look like this. And I actually want it in terms like this when I'm dealing with this proof, because it's going to make it easier to work with. And so now I'm just going to say that dy dx, I'm going to move this factor to the other side. This is going to equal cosine squared of y divided by sine of y. And if I plug in my y value here, this is going to be equal to cosine, wrong letter, cosine squared of secant, inverse secant of x divided by sine of inverse secant of x. And now what I want to do is I want to construct a triangle where inverse secant of x is equal to theta. And well, how would I do that? I would have to construct a triangle where secant of theta is equal to x. And if secant of theta was equal to x, if secant theta was equal to x, and I took the inverse secant of both sides, the inverse secant of secant theta is just going to be equal to theta. And then on the right side here, we would have this is equal to the inverse secant of x. And so if I can construct a triangle where secant of theta is equal to x, then I can use this fact here to just plug in theta into this equation, and then I can use cosine and sine on that triangle, which is very easy to work with, in order to finish out this proof. And so how could I go about constructing a triangle where secant of theta is equal to x? Well, if secant of theta is just hypotenuse divided by adjacent side, then I can just set the hypotenuse equal to x, the adjacent side equal to 1, and then by Pythagorean theorem I can very easily figure out this third side, 1 squared plus, let's just say that the length of this side was equal to a squared is equal to x squared. Solving for a, I would get this is equal to the square root of x squared minus 1. And so I can plug that in there. I can plug that in here. The square root of x squared minus 1. And now, everywhere that I see a inverse secant of x here, I can plug in theta, because secant of this theta is going to be equal to x over 1. That's just x. So inverse secant of x is going to equal this angle theta. So now I have that dy dx is equal to cosine squared of theta on this triangle divided by sine of theta on this triangle. And now you can see cosine squared of theta. Well, that's easy. Cosine is just adjacent over hypotenuse. So that's 1 over x squared. So this is going to be 1 over x squared. And then we have to multiply by 1 over sine of theta. 1 over sine of theta. Sine of theta here is just going to be equal to opposite over adjacent. So that would be square root of x squared minus 1 divided by, or opposite over hypotenuse. So it's going to be square root of x squared minus 1 divided by x. And so 1 over sine of theta is going to equal x over square root of x squared minus 1. And so when I take the product of 1 over x squared with x over square root of x squared minus 1, one of these x's is going to cancel with this one over here, and I'll be left with 1 over x times the square root of x squared minus 1. And this is almost correct, but we need to be very careful here. On a triangle, these side lengths cannot be negative values. So I can't just plug in a negative value for x here, because, okay, this side length, if I plug in any value of x, it's going to be equal to a positive number or a number that doesn't exist. You know, here x has to be greater than 1. But in general, this x squared term here is going to maintain, it's going to keep this side length being positive. But here I have an x value, just x on its own, and if I plug in a negative value here, this formula is going to fall apart because it's dependent on this geometry of the triangle. And so I'm actually not quite done. I need to say that this is equal to 1 over the absolute value of x maintaining that this side length here of this triangle is always positive. You can't have a negative side length of a triangle. And then it's not necessary here because we have an x squared term, but now we are finished. And this is the derivative of inverse secant of x. So the derivative for arc cosecant is going to proceed in a very similar fashion. We can go a little bit quicker through this. So once again, we're just going to do cosecant of y is equal to x here. And we're taking the derivative of this entire expression with respect to x. When we take the derivative of the left side here, I just want to remind ourselves what the derivative of cosecant is. Cosecant of y would be the same thing as sine of y to the power -1, and the derivative of that is going to be equal to -1 over sine squared y multiplied by the derivative of this inside function here. The derivative of sine of y with respect to y is going to be cosine of y. And then we need to multiply once again by the derivative of this inside function. It's like a nested chain rule of dy dx. So plugging this information in over here, and then the derivative of this right side here is just 1. It's the derivative of x with respect to x. We've done that 1,000 times in this video. So we have cosine of y over sine squared y, negative cosine of y, sine squared y, multiplied by dy dx is equal to 1. We have dy dx is equal to negative sine squared y over cosine of y. And this is equal to negative sine squared of, let's make it explicit and re-plug in our expression for y, cosecant, inverse cosecant of x, divided by cosine of the inverse cosecant of x. And so similarly, I want to construct a triangle where inverse cosecant, sorry, that's so bad, where inverse cosecant of x is equal to theta. We take cosecant of both sides, we get that x is equal to the cosecant theta. And so I want to construct this triangle where cosecant of theta is equal to x, so that will allow me to plug theta in to this expression, just like we did in the last video. So what's cosecant? Well, if sine is equal to opposite of over hypotenuse, then cosecant is going to equal hypotenuse over the opposite side. Hypotenuse would be equal to 1, or x, and the opposite side would be equal to 1. And now cosecant, if this is theta, cosecant of theta is going to be equal to x. And so what is the side length here? Well, actually, it's exactly the same as the last triangle. It's going to be the square root of x squared minus 1. And now we just plug in theta here for inverse cosecant of x, and we get that dy dx for the arc cosecant of x is going to be equal to negative sine squared of theta on this triangle divided by cosine of theta on this triangle. What is negative sine squared of theta in this triangle? Sine is going to be 1 over the hypotenuse, which is x. So this is going to be -1 over x squared multiplied by 1 over cosine of theta. That's just secant theta. Secant theta on this triangle is going to be x over x square root of x squared minus 1. So this would be x over the square root of x squared minus 1. And we get for our final answer -1 over x square root of x squared minus 1. So this is just the negative derivative of inverse secant of x. Interestingly enough, but that's the proof for it. And I almost forgot, so you do have to be careful to remember, just like in the last proof, there cannot be a negative side length here. And so even though we have this square root of x squared minus 1, which is always going to be a positive or imaginary value, but let's not concern ourselves with the imaginary part, this will always be positive, we need to add the constraint that this side length is also always positive, because this is borrowing on the geometry of a triangle. And so we need to make this the absolute value of x. And that is the correct answer to the derivative of the inverse cosecant of x. All right, last but certainly not least, in our examples of implicit differentiation, we have the derivative of the inverse cotangent of x. And this one's a little bit simpler than inverse secant or inverse cosecant. It's going to start the same way. We have cotangent of y is equal to x. Then we're taking the derivative of both sides with respect to x. Derivative of cotangent of y is going to be negative cosecant squared of y multiplied by the derivative of that inside function dy dx. And the derivative of this right side here with respect to x, once again, is just equal to 1. And so we have dy dx is equal to negative 1 over cosecant squared of y. And if you were to take 1 plus cotangent squared of theta, that would be the same thing as cotangent squared of theta would be cosine squared of theta over sine squared of theta. And if we're adding 1 here, that would be the same as adding sine squared of theta over sine squared of theta. And then this would reduce down to 1 on the top, 1 over sine squared of theta. And this is just equal to cosecant squared of theta. And so 1 plus cotangent squared of theta is equal to cosecant squared of theta. We can just plug this identity in here, and we have that cosecant squared of theta is going to equal 1 plus cotangent squared of theta. So we can plug that in here. This is equal to negative 1 over cotangent squared of y plus 1. And if we take cotangent squared of our y here, which is inverse cotangent of x, this would reduce quite nicely to negative 1 over x squared plus 1. And that's our derivative for arc cotangent of x. So I hope that was a little bit illuminating. I hope that we went over all of the inverse trig functions. We went over logarithms with any sort of generic base. We also went over the natural logarithm, and we proved the power rule for fractional exponents. So we got a lot of different practice here with implicit differentiation, but we also expanded our knowledge of different derivatives. So we kind of do those things simultaneously. Hope it helped. Thank you guys for watching. I'll see you in the next one.